Welcome to Bite Size Tutorials, where we break down complex topics into quick, easy to digest lessons. Let's talk about consistent hashing, a smart way to distribute data across multiple nodes in distributed systems. It's the backbone of technologies like distributed caching, load balancing, and databases like Cassandra and DynamoDB. Let's dive in. Imagine you have a bunch of servers and you want to evenly distribute your data across them. Normally, you would hash the data and spread it across the servers. But here's the problem: what happens when you add or remove a server? With a typical approach, adding or removing a server might require all your data to be reshuffled, which is inefficient. Interconsistent hashing, which minimizes data movement when servers are added or removed, keeping the system efficient and scalable. Here's how it works. First, picture a ring, a circle that represents a large range of hash values. These values span from 0 at the top of the ring to a large number, let's call it n, at the top again, completing the circle. This large number depends on the hash function being used. For instance, a 32-bit hash function would have approximately 4 billion unique positions. Next, we hash each server and place it on this ring. For example, if we hash node A, it might land at position 120 and node B might land at 300. To improve load distribution, we can assign multiple positions to each server on the ring. These are called virtual nodes. Now, let's say you have some data like the key user123. We hash this key and place it on the ring 2. The rule is simple. The data belongs to the first server you encounter when moving clockwise around the ring. For instance, if user 123 hashes to position 250, it's stored on node B because node B is the next server clockwise from 250. Now let's see what happens when you add or remove a server. Let's say you add a new node, node C, and its hash lands at position 200. Node C takes responsibility for the data in the range from 128 to 121 to 200, the portion previously owned by node B. This means data like user 456, which hashes to 150, now moves to node C. Other data like user 123, which hashes to 250, stays with node B. This is the magic of consistent hashing. Only the keys in the range between node C and the previous node A, are affected. Everything else remains where it is. Similarly, if you remove a node, its data simply shifts to the next server clockwise. For example, if node C is removed, its range of keys, that is 121 to 200, would move back to node B. No more reshuffling all your data. This makes consistent hashing scalable and perfect for systems that need to handle dynamic changes. It's used in distributed caching systems like memcached, databases like Cassandra, and even load balancers. But there's one catch: hotspots. If nodes aren't evenly distributed around the ring, some nodes might get overloaded. That's where virtual nodes come in. By assigning multiple positions to each server, we can spread the load more evenly. To wrap up, consistent hashing is a brilliant way to distribute data in dynamic systems. It minimizes disruption, ensures scalability, and works seamlessly across systems like distributed caches, databases, and load balancers. If you found this tutorial helpful, give it a like, share it, and check out more bite sized concepts in our series. See you next time.